Group 7, project number 4. I'm Aiden Passmore.
I'm Joseph Riddell.
And I'm Reed Johnson. My name is Reed Johnson, and I'll be going over the first part of the project, which is thermal expansion. Thermal expansion is a material's tendency to change size with temperature. All materials have thermal expansion coefficients. It's generally a positive number. That's an indication of how size changes with temperature. How it works. As heat is put into a material, its energy level increases on the potential energy graph. As energy increases, there are two possible R values. The atoms oscillate between the two values, but as energy increases, the average of the two possible R values shifts to the right, causing an increase in size overall. You can kind of see what I'm talking about on this potential energy as a function of interatomic distance curve over here. This would be the minimum of potential energy, and as you add energy, you can see that there are 2 points where the interatomic distance can equal that energy. So the atoms oscillate between these 2 points, and as you get more and more energy, you can see that the average is shifting to the right more and more.
Now moving on to the calculation part, we have a 1 meter iron bar and a 1 meter aluminum bar clamped in series between two rigid walls at 20 degrees Celsius, as seen in the left picture. Now the temperature of both metal bars are going to be increased by 100 degrees Celsius. And we want to find the final length of the iron bar, the final length of the aluminum bar, and what their final stresses will be. So we're going to start by finding the stress with the equation stress equals the negative change in temperature times alpha Fe plus alpha Al over 1 over the Young's modulus of iron plus 1 over the Young's modulus of aluminum. And we're given the alpha Fe as 12 times 10 to the negative 6 per Celsius, and alpha Al as 23 times 10 to the negative 6 per Celsius. We're also given the Young's modulus, and to find the change in temperature, we do final minus initial, so 120 minus 20, which gives us 100 degrees Celsius. Now plugging into this equation, we get the stress equals negative 100 times 12 times 10 to the negative 6 plus 23 times 10 to the negative 6 over 1 over 200 times 10 to the 6 plus 1 over 70 times 10 to the 6. And that'll give us that our stress equals negative 1.814 times 10 to the 8 pascals. And the negative just means that it's in compression, which is what we should expect to see. Now moving on to find the length, we're going to use the equation. The final length is equal to the original length times 1 plus alpha times delta T plus the stress over the Young's modulus. Now we can go ahead and plug into this equation. So we have the final length for iron is equal to the original length, which is 1 times 1 plus 12 times 10 to the negative 6 times 100 plus our stress is negative 1.814 times 10 to the 8 over 200 times 10 to the 9. And that will give us a final length of 1.000296 meters. So as you can see, it just barely got bigger. Now we're going to move on to the final length of aluminum, which is equal to the original length, which is 1 times 1 plus 23 times 10 to the negative 6 times 100 plus our stress, which is negative 1.814 times 10 to the 8 over 70 times 10 to the 9. which, if you plug that into your calculator, will give you 0.9999707 meters.
The diffusion flux equation is an equation that describes the flux of diffusion across a certain cross-sectional area based off of the change in concentration. So we have our J is flux, our D is the diffusion coefficient, and the C is the concentration. So J equals negative D times the derivative of C. In our simulation, we see that when the concentration on the left side is high, our flux is higher. We can see this in our data over here, where a change of there's a change of 48 dots or atoms from 0 to 48 here in the first 10 picoseconds. And then the last 10 picoseconds of the 200 atoms, we only see 22 move over. In the 100 atoms, we see the same kind of trend. We see 21 move over in the first 10 picoseconds, and then again about half of that number, only 12, move over in the last 10 picoseconds. So we see that when the concentration on the left is high, the flux is high, and the flux decreases as the concentration evens out, and that is proven in the simulation. Here at the end, we see it teeter around the halfway point, around 100 for the 200 atoms, and around 50 for the 100 atoms.
Alright, I'm Aiden, and I'm doing the diffusion coefficient part of the project. I was given the equation D equals D naught times the exponential of negative ED over KB times T. So this equation is how you find the diffusion coefficient using a given diffusion coefficient, the activation energy, and the Boltzmann constant, along with temperature. This shows the relativity between temperature and the diffusion coefficient, which also shows the relativity between temperature and then the flux. So in this, D equals the diffusion coefficient, ED is the activation energy, KB is the Boltzmann constant, and T is the temperature in Kelvin. Use KB in this since we're doing it on the atomic scale, where if you were doing it per mole, you would use R. In order to prove or disprove that this equation works for our data, we first need to look into how the thing works. In the end, it will prove it, but based on the equation, since e to the negative ed over kBt, as t increases, the value of d would get larger because e is to the negative exponent. If e was to a positive exponent, it would make it smaller, but since it's negative, it makes it a larger value. So a larger value of d would mean that more atoms would cross over the barrier over the 30 seconds. And this is true because over the 30 seconds, the experiment, when it was at 300 Kelvin, we had 106 atoms cross over from the left to the right side. And while we were at 50 Kelvin, we only have 55 atoms crossed. This does prove that there is a correlation between temperature and the diffusion coefficient, where as temperature decreases, less atoms cross, and vice versa. As temperature would increase, more atoms would cross, which shows the total energy increasing the speed, and thus the flux of the atoms.